Pluto, a far-off and elusive planet, used to be part of our nearby solar system, but recent unsettling comments from prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have thrust it back into public focus with a startling revelation. Both scientists propose that this icy body could be on a potential collision course with Neptune. But how could such an event even be possible, and what would the consequences be for us? Could this be an extraordinary cosmic anomaly, or is there something deeper at play regarding this approaching celestial disaster? Join us as we delve into the possible outcomes of a Pluto-Neptune impact. Pluto, which was once considered a full-fledged planet before being reclassified as a dwarf planet due to its unusual orbit, continues to be a fascinating subject for research in the scientific community. Recent predictions from leading experts suggest that Pluto's orbit may be alarmingly close to Neptune's orbit. Both Tyson and Kaku have raised concerns about the potential for a catastrophic collision between the two planets, which could spell significant danger for Earth. But how is this even conceivable? Pluto's path around the Sun is unlike that of any other planet in our solar system. It takes an extraordinary 248 years to complete a single orbit. Since its discovery in 1930, it has yet to finish one full revolution. However, Pluto's orbit stands out for more than just its length. It has a highly elliptical trajectory, straying far from the nearly circular orbits of the main planets. Adding to this uniqueness is Pluto's inclination, which is tilted at an angle of 17 degrees relative to the ecliptic plane. This results in an orbit that is much more extreme compared to those of the other planets in the system, complicating its movement through space. One of the most intriguing aspects of Pluto's orbit is the fact that it intersects with Neptune's path. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune, which defies the expectations based on their positions within the solar system. Naturally, this raises the question, why hasn't Pluto collided with Neptune already? The answer is rooted in the gravitational influences of other planets. Astronomers began studying Pluto's orbit right after its discovery, trying to understand its unconventional path. Unlike other planets, whose orbits are relatively flat and close to the ecliptic plane, Pluto's orbit is tilted steeply and elongated. The mystery grew deeper when it became clear that Pluto's orbit does, in fact, cross that of Neptune. Despite this, Pluto's orbit remains stable, a testimony to the intricacies of celestial mechanics. The interaction of Pluto, Neptune, and the Sun follows a concept in astrophysics called the three-body problem. This problem deals with determining the movements and interactions of three celestial bodies based on their gravitational effects on each other. In Pluto's case, this includes how its orbit, Neptune's orbit, and the Sun's gravity influence one another. Key to understanding Pluto's stability are the concepts of ASU libration, degree libration, and VZK oscillation. According to astrophysicists, ASU libration is what keeps the orbits of Pluto and Neptune from colliding. It ensures that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune, creating a critical separation that prevents a collision. Degree libration, on the other hand, involves the vertical movement of Pluto in its orbit, meaning that when Pluto nears Neptune or any large planet, it is located far above their orbital plane, further reducing the risk of an impact. The VZK oscillation, a term named after scientists Zell and Kai who studied the movement of space objects, helps explain why Pluto's orbit, despite its apparent erratic behavior, moves in a relatively smooth manner over long periods. The oscillation shows that while space may appear chaotic, underlying forces maintain order and stability. All these forces work together to prevent Pluto from colliding with Neptune or deviating from its path. Despite these stabilizing mechanisms, studies from the late 1980s revealed that Pluto's orbit is still somewhat chaotic. Minor changes in its initial conditions can cause significant alterations over thousands of years. Nevertheless, these variations are controlled enough to ensure Pluto's orbit remains relatively stable over long periods. Later computer simulations have helped astronomers understand how the gravitational pull of giant planets like Neptune, Jupiter, and Saturn impact Pluto's movement around the Sun. Neptune and Pluto share a unique orbital relationship. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This alignment helps maintain Pluto's stability, but it isn't just Neptune that plays a role. Jupiter's gravitational pull also stabilizes Pluto's path, as does Saturn's. Simulations indicate that Jupiter's gravity is strong enough to maintain Pluto's orbit over millions of years, ensuring its continued stability and preventing catastrophic collisions. These gravitational relationships are vital for maintaining order within the solar system. Without them, the system could become much more chaotic, with bodies like Pluto potentially colliding with others or being ejected from their orbits, causing a ripple effect throughout space. In the case of Pluto, understanding its orbit becomes crucial when considering the possibility of a collision with Neptune in the future. It serves as a reminder of how dynamic and unpredictable the solar system can be, and highlights the delicate balance of gravitational forces at play. The study of Pluto's orbit shows us that even seemingly unstable orbits can achieve a state of equilibrium through the interaction of gravitational forces. This complexity underscores the need for continuous observation of space, as it helps us better understand our place in the cosmos. Pluto's case exemplifies how space exploration often leads us to confront the bizarre and unexpected characteristics of celestial bodies. The concept of orbital chaos is clearly demonstrated in Pluto's case, which shows how sensitive a celestial body's orbit is to its initial position and speed. Small adjustments in Pluto's location or velocity can drastically change its long-term trajectory. By running simulations, researchers have been able to better understand how Pluto's interactions with other objects like Neptune influence its movement through space. These simulations show how tiny changes in the starting conditions can lead to vastly different orbital paths, making precise predictions about Pluto's future movement an incredibly challenging task. In the late 1980s, these simulations revealed that, despite Pluto's mechanisms for maintaining a stable orbit, its trajectory could still be highly unpredictable over long stretches of time. Even though it may seem turbulent at times, Pluto's path around the Sun follows an order beneath its apparent chaos. This paradox makes predicting the future of planetary orbits a daunting task. The unpredictable nature of planetary orbits like Pluto's reveals the inherent volatility of space systems. While mathematical models can help us understand and predict these orbits, they are limited by the accuracy of initial conditions. A small error in these conditions can cause large deviations in the outcome, which complicates long-term predictions. The chaotic behavior of planets like Pluto serves as a reminder of the dynamic and ever-changing universe, and our ongoing quest for knowledge. Studying how the giant planets influence Pluto's orbit offers valuable insights into the broader mechanics of our solar system. It shows how the gravitational effects of each planet can dramatically affect the motion and stability of others. This brings us back to the question: why are leading astrophysicists like Tyson and Kaku expressing concerns about a potential Pluto-Neptune collision? Despite the stabilizing forces in place, Tyson, a renowned astrophysicist and cosmologist, offers an interesting viewpoint on Pluto's future. Tyson, known for his involvement in the demotion of Pluto from planet to dwarf planet status, believes that the evolving nature of our understanding of celestial mechanics means that we should continue to monitor Pluto's situation closely. Tyson emphasizes that the orbits of Pluto and Neptune will continue to change over time, driven by forces that are sometimes unpredictable. He acknowledges that Pluto could gradually get closer to Neptune over millions of years, although he remains cautiously optimistic about the likelihood of a direct collision. Tyson suggests that while such an event is unlikely in the short term, the chaotic nature of planetary orbits means we cannot completely dismiss the possibility of a collision in the distant future. Michio Kaku, another leading scientist and theoretical physicist, adds his perspective on the potential consequences of a Pluto-Neptune collision. Kaku, who has a deep understanding of the evolution of the cosmos, notes that such a collision, if it were to happen, could have far-reaching effects, not just for Pluto and Neptune, but for the solar system as a whole. He points out, however, that the vastness of space and the complexities of their orbits make a collision in the near future extremely improbable. Still, the idea remains an intriguing topic for further scientific exploration. In conclusion, the possibility of a Pluto-Neptune collision is an ongoing subject of debate among astrophysicists. While the mechanisms of their orbits prevent an immediate collision, the unpredictable nature of celestial dynamics means we cannot entirely rule out the possibility in the distant future. The changing orbits of planets like Pluto remind us of the dynamic and unpredictable nature of the universe. Whether such an event occurs or not, it stands as a fascinating example of how much we have yet to learn about the future of our solar system. The case of Pluto highlights just how much is still left to uncover about our solar system. The unpredictable movement of celestial bodies like Pluto serves as a reminder of the constant flux in space. Despite all the mathematical models and theories, there's still so much that we don't know, and Pluto's orbit is a perfect example of this. While it may seem that our understanding of space is complete, Pluto's trajectory continues to reveal new mysteries that challenge existing ideas. The ongoing study of Pluto and its interactions with other planets, like Neptune, is crucial for refining our knowledge about the broader mechanisms that govern celestial bodies. As we look further into the future, we must recognize that the very nature of our solar system is in a state of constant change. Even though the chance of Pluto colliding with Neptune might be small in the near future, the vastness of time and the complexity of orbital mechanics mean that this event cannot be ruled out entirely. Over millions of years, the positions of planets and their gravitational influences will evolve in unpredictable ways. It is this sense of uncertainty that makes the study of space so fascinating. Every discovery leads to new questions, and the answers are often more complex than we could have imagined. The continuous observation of Pluto and other celestial bodies within our solar system plays a key role in helping us understand how gravitational forces, orbital mechanics, and the interactions between various objects shape the cosmos. The fact that Pluto's orbit, despite its seeming erratic nature, is still relatively stable over such long periods, is a testament to the intricate balance of forces at play in space. As scientists continue to study these forces and refine their models, we gain deeper insights into the future paths of planets and other celestial bodies, helping us to make more accurate predictions about the long-term evolution of our solar system. While the possibility of a catastrophic event like a Pluto-Neptune collision remains unlikely in the short term, the ongoing research serves as a reminder of the dynamic and unpredictable nature of the universe. Whether such an event will occur or not, the very fact that it is even a topic of discussion underscores the complexity of celestial mechanics and the continuous need for scientific exploration. In the end, the story of Pluto serves as an example of how little we truly know about the cosmos. Even as we make significant strides in understanding the mechanics of the solar system, new questions emerge, and the answers we find often lead to more mysteries. As we continue to explore and study Pluto, Neptune, and other celestial bodies, we move closer to a more complete understanding of the universe, while simultaneously realizing that the journey is far from over. The more we learn, the more we discover just how much there still is to uncover.